Good afternoon, and hello again for the people who did 4C16, and hello for the new people that haven't seen before. So my name is François Pitié. I'm Ussher assistant professor in electrical engineering, and so welcome to 4C8, which will be a course mainly on image and video compression. Okay. So as I said, so we're going to look at the fundamentals of signal processing and that you apply for images. Okay, so in that sense, you can see a 4C8 an extension of all the signal processing you've done in third year, and kind of extend it to from 1 dimension to 2 dimensions. So for the people who did 4C16, this is kind of like the classic old school image processing. Okay, this is image processing before the advent of deep convolutional neural nets. So in this course, we're going to look at some of the classic compression algorithms. So you have for images, so such as JPEG, and as well for videos, such as MPEG-2 and MPEG-4 and so on. Right, so I just want to check that the timetable is correct. I just pulled that from the timetable, so I think it should be correct. A slight change, okay, so the labs, this is from 9 o'clock to 11 o'clock, okay? I cannot be here at 9 o'clock, I'll be here at 9:30, so the lab will be open at 9. Hopefully the labs will be quite short anyway, so it shouldn't be a problem, so you can come at 9:30. So the remaining 3 lectures will be mainly about lectures and a bit of tutorials as well. So the labs, they're marked, and that will contribute to 25% of your final mark. So about the exams will be exactly the same as last year's, or exactly slightly different, okay? But so it's not, there won't be any change, okay, from previous years. Right, so looking back at the prerequisite for 4C8, sorry. So you look back at, maybe 3C1, if you know about the Z transform, convolution, Fourier transform, and so forth, be very useful. I will come back to that, okay? So I will, we'll go slowly enough, but you get a refresher on those. And we'll touch on information theory, and that's because you're using compression, so entropy and shell encoding and so on will be useful at a point. But then again, I will go slowly for that, and you'll get ample information in the material just for 4C8. Okay, and so a slide note as well. This is not a new course, so this course existed before, and in fact really was originated by Professor Anil Kokaram. So probably 80% of the course material is derived from that, which itself was derived from a course from Cambridge back in the day. So this course has a bit of a history. The good news is image compression and video compression hasn't changed too much in its core components, and you would think that, say, with deep learning and so on, things will change dramatically, and probably not, because chances are that in the next 20 years' time, people will still have MPEG-2 videos, people will still be using JPEG, and so on and so forth, because what we've seen in previous years that when you have new codecs or new technology, the old one doesn't disappear, okay? So if you look at YouTube, the amount of video format they have is gigantic. We have 100 different types of video codec coming to them, uploaded every day, and the old one, the first one, MPEG-1 and so on, are still being uploaded on a daily basis. So all what we talk about today is relevant today, and was relevant yesterday, and will be relevant in the next 10 years, okay? So just wanted to start with this this short video from YouTube that shows some of the work that actually people from the department have been working on. So this is, so as you might know, some of the people in our team have been acquired by Google and YouTube a few years back, and they moved to YouTube, and some of the work you've seen here will actually be work that was done by people from our team going into YouTube. And this video by the end of the course, you'll understand most of what's going on here and gives you a glimpse of what is happening in real life.
Hey there, I'm Nat.
And I'm Lo.
And we make a YouTube show about everything you never knew you wanted to know about Google or something like that.
And this is part 2 of a 2-part episode about how YouTube works.
In part 1, we go into what happens when you upload a video. If you'd like to watch that, you can check out the link in the video description.
And in part 2, we learned what actually happens when you watch a video.
We didn't know the answers when we set out to make this video, so we talked with a couple of YouTube engineers, Richard and Steve and Bernard. If you're like us when we started working on this, you might think that when you press play on a video, YouTube is just grabbing that video and playing it for you. And that's how YouTube used to work.
What used to happen 10 years ago when you watched a YouTube video, there was one file, and we would just download it. And sometimes you'd watch that spinner, and it was very interruptive.
So YouTube decided to do something about this, which they codenamed sliced bread.
Sliced bread, as a sort of metaphor, means break the video up into pieces, and so you can lay down the track for the train as it's rolling. And every time you get a piece, you decide what's the size of the next one you're going to use. And we call this adaptive bitrate.
Adaptive bitrate just means that the size of your video slices can change on the fly, which is helpful because your internet bandwidth is frequently changing.
This one. How this works is when you press play on a video, YouTube is immediately analyzing your situation.
Is your network good? How big is your screen? How much have you downloaded already?
It might decide, hey, things are pretty good. So here's a high-resolution video slice to start things off. And here's another one and another one. But then, let's say your brother comes home and starts downloading this huge file, so your bandwidth is constrained and YouTube needs to downres your video slices to make sure that the video you're watching doesn't have a lot of buffering.
For the most part, YouTube playbacks are smooth, but when they aren't, it's really, really irritating. And we hate that as much as anybody. And every day we're trying to make the time that the spinner shows just a little bit smaller.
Another thing that can speed up how fast videos play is where physically those video files are coming from.
It's easy to think of YouTube as a single thing, where all the videos sit in a giant pile. But in practice, when you watch a video, it gets a little bit closer to you.
More formally, this is called YouTube's Content Distribution Network. YouTube partners with the companies you get your internet from. They give them a rack of hard drives, essentially a box, for temporary storage of videos.
And when you go to request a YouTube video, instead of going to Google's central servers, you're actually going to that box.
So when you press play on a video, the first thing YouTube's going to do is check the boxes closest to you to see if they have that video.
Your browser will send a request, say, hey, give me that video.
If it's popular, it probably has it. But if the box doesn't have that video, because the video is just uploaded and has 0 views, or it's never been viewed in that location, then the box says,
Never heard of that video before. So it turns around and talks upstream.
And along the way, if none of the boxes have that video, the system grabs that video
From a disk somewhere in the Google data center, send it back down and say, here, you have a video, go ahead.
And what's amazing is that this all happens organically and automatically just based on who's watching what where.
I think of it like a tree. The root is in the storage, and then from there it branches out through all parts of the world.
Is that why you wore that t-shirt?
Sheer coincidence.
Because people like you love to watch lots and lots of YouTube videos, including this one, thank you very much. The ever-growing size of YouTube is hard for even the engineers to wrap their heads around.
The scale is mind-blowing. The amount of network traffic that we do, the amount of storage that we need to deal with, it boggles my mind.
Do you have a favorite part of YouTube?
I love videos. I love that people make them. I love how they're transmitted. I love it all.
Humans are weird and wonderful and creative. YouTube being a video site has sort of just allowed the weirdness to be documented and become popular. YouTube is a place where all of those moments can be preserved. Anybody can make them. And we will hopefully be showing those to everybody forever.
Thanks for watching. If you haven't, check out part 1, where we talk about what happens when you upload a video, and subscribe to our channel if you like what we're doing.
All right. Okay. So it's going to give you a glimpse of what is actually happening once the transcoding has happened and so on. Right. So let's come back to the basics, okay? So we can talk about pictures. So picture is made of pixels, okay, so you know that, and each pixel is made of 3 colors, so 3 values for red, green, and blue components. And usually those are coded into 8 bits, so you have 256 different values, so starting from 0 to 255 at the maximum. And so it's an additive model, so the bigger the value is, the more, say, blue you have, okay? So when I talk about the resolution, the first number, so say 600 by 400 pixels, the 600 is the width of the picture, so the number of pixels you have on the width, and 400 is the number of pixels you have on the height. Coming back on the bit depth, or the number of the resolution of the color, if you want. So it's 8-bit, but sometimes it could be floating point, okay? So when it's floating point, usually you have a value between 0 and 1, which is a continuous value, floating point value, and if it's otherwise not a floating point value, if it's an integer, so 8-bit, that would be an integer between 0 and 255, or if it's 16-bit, between 0 and 65,000 or something, okay? Right, so historically, the first case of digital images was in the 20s, okay? So it's quite a while back, and the first case of using digital image processing in cinema, for instance, for post-production was actually in 73 with this movie called Westworld. And then closer to us in the 80s, there is this big war between digital beta and VHS and so on to know how you can save data, but the main points, like the digital video tapes, were actually created as well. So anyway, so moving on, so we had digital television and DVDs, and then close to us, mobile phone, and started to kind of take over the way we consume videos. And then nowadays we're talking 4K HDR and all sorts of things, and most of the video consumption we do, of course, is through streaming from Netflix and YouTube and the like. Right, so in the course we'll have a few points about the historical aspect of things, how we come about doing, capturing pictures and so on. So why do we talk about compression, okay? There's another, I'll try to make a point here that you cannot live without compression, okay? This is required, okay? So the types of resolution you have, so when you look at a video, there's a number of different sizes that people use, okay? So if you look at an old TV, say in PAL, so when you were born, you still had TV that was not HD, okay? And that was called standard definition, okay? So PAL, the format, the Hertzian videos, Hertzian TV, sorry, was broadcasted in what's called standard definition. And that standard definition was 720 pixels per line and 576 lines, okay? So you had a picture of 720 by 576. And you had 3 colors, and each of them are represented in, say, 8 bits. And if you do that at 25 frames per second, you end up with a bandwidth of raw material at 250 megabits per second. Okay, so it's quite, it's starting to be quite a lot. Definitely, if you have to stream, even nowadays, on your mobile phone, 250 megabits per second, it's quite a fair bit. When you move to HD, and the bandwidth now is 3 gigabits per second. Okay, so definitely you want to have a very, very good internet connection for that, right? And if you move to when you go to cinemas, the quality you have to cinemas, so already like you don't work in HD anymore, you work maybe in 4K, and the resolution, you don't work in 8-bit anymore, but probably in 12-bit, so you have more colors basically to express your picture, and you don't work in 25 frames per second, maybe 48 frames per second. And you have 2 views because it's in 3D, so you have times 2, right? And now you have 30 gigabits per second, all right? So you need a good computer at that point, right? So here's the problem, okay? Right now, video streaming, so actually these numbers were from 2015, but still valid today. it's at least 60% of the internet, okay? So in some countries, say YouTube takes 80% of the internet, right? So if you combine YouTube and Netflix and say BBC and all these guys, you can be sure that they take at least 50% of the internet, okay? The entire bandwidth of the internet, right? So it's huge. So when you look at compression, you look at compression a different way. Like you say, I make a very small 1% improvement of your algorithm. Well, that could have massive consequences on the entire bandwidth of the entire internet, okay? So it's kind of, even a small number has a massive impact, okay? And that's still relevant today. It's more and more relevant as we speak. But here's a problem, okay? So we can say, right, bandwidth is getting better. 5G is around the corner. We have super fast 1 gigabit connections and so on. We'll catch up, right? But the answer is no, we won't catch up, because every third year, whatever, we seem to increase the resolution of the videos. On the top left here, the SD is standard definition. Okay, that's a TV you watched 15 years ago. Okay, 10 years ago. HD is not much bigger. Ultra HD is that we see most of the days. Like if you buy a TV set, probably would be 4K. All right, so that's a bit bigger. And now 8K is actually quite common. All right, so YouTube is streaming 8K, and so that's already done. That's as of last year. Okay. Look at the difference between 8K and SD, right? So every time we double the size, we actually quadruple the amount of pixels we have and quadruple the bandwidth and so on. So you'd be like, okay, 8K, for instance, in cinema, the resolution that your eye can resolve is about 2K, okay? If you go to 4K, you don't get much more than you can think. But there's still always applications for 8K, right? And it's not only that, but so resolution is just one aspect, okay? The other aspect is the bit rates, the bit depth, sorry. So the bit depth, what I say, is like you represent the colors, each color, by usually an integer between 0 and 255. But we know that's not good enough, okay? So if you have, say, a gradient of gray going from black to white, then you have 255 steps, and your eye will start to see the steps, okay? So what we've come up in the last year, and you can see that now, it's out on the market, it's the advent of HDR TVs, so they stand for high dynamic range. And basically what it means, like instead of using 8-bit pixels, we're going to use 10, 12, 14, 16-bit pixels, okay? So basically we have more colors and richer colors, and as well that comes in HDR as well. Usually you have darker darks and much brighter brights, okay? So you almost need sunglasses to watch TV these days, okay? But that's the point, okay? So you increase as well the bit depth, so you double the amount of information you have. And this is not the end, okay? So if you look at VR, so quite a lot of money has been poured into VR, and to capture VR, basically what you need to do is to capture the scene from every single possible angle, okay? This is the Odyssey system by Google that was released last year. So basically you have 16 GoPros on a circle, and each of the GoPro sees a different angle from the scene, and then after you do a lot of maths and reconstruct pictures, and you're able to be as if you were actually in the scene and be able to kind of move slightly around and turn your head and still feels like you're in the scene. Now, when you go to VR, basically if you want to have realistic VR, you need at least a resolution of 16K, all right? Because at any given time, when you're in your headset, you're only going to see some part, a limited field of view of your scene. So if your entire scene is 16K, what you only see at is maybe like 2 to 4K, right? So if you want to see 2 to 4K in resolution, the entire scene has to be at least shot in 16K, right? Now 16K, it's a lot of pixels, right? And of course you want 120 frames per second because that's what you want, okay? So now you have 1 terabits per second. Okay, your mobile phone might not like that. Okay, and then you have light field. Now I love light field. I think light field is a feature of imaging. Okay, basically here in VR you had 16 cameras. It's good, but we can do better. Here we have, I don't know, 100 cameras shooting a scene. Okay? So why not have as many cameras as you can have? And the idea is, basically, you want to be able to say not only that this pixel is red, but we want to know where it came from. We want to know the angle, where the incidence from that ray of light. We want to be able to reconstruct the entire what's called light field. Okay, so the entirety of where the photons come from, which angle, where it was, and so on. Okay, because if we know that, then really we can recreate an immersive experience, and we understand a lot more about what's going on, and we can do cool stuff like say. You can shoot a scene and not worry about where the focus is. And then you can defocus wherever you want, change the lens, and create virtual lens, and all sorts of cool stuff. Anyway, it's kind of the future, okay? But, 14 terabits per second, okay? Not good, okay? So the thing is, you want compression. Everybody uses compression. Nobody works with raw images, okay? So even if you are working for cinema post-production. So cinema post-production companies are, say, like the likes of ILM or Weta Digital or Double Negative in London. They're the people making the movies, okay? And you'd be like, right, they make movies, they really care about the pixels, they don't want to compress the images, right? Well, they do, okay? And it starts from, they have a variety of algorithms. It's true, usually they use lossless compression algorithms, so they don't destruct the pictures, but they still have some amount of compression, and they're very important for that to happen. I would even make a case that it's not just saving some space or saving some bandwidth, okay? It's about the ability to be able to process that data. When you have a camera, even the most expensive camera, say like Arri Alexa, which is a very expensive camera that would cost 100,000 euro, that people use on film production, you never get access to the raw material, okay? Because on the chip, the first thing they do is to compress the data, because even within the camera, they just cannot deal with that much data to go through in the pipeline. So the first thing that you do on the chip is to actually compress the data, right? And it's not lossless, it's actually, lossy compression. You actually lose some of the data. And it's kind of inevitable. Like because you just cannot deal with that much data, even at a hardware level, you cannot just have the bandwidth is just very important. And here we're talking different kind of bandwidth. We're not talking IP bandwidth. We're talking bandwidth between your GPU and your CPU, for instance. Okay, so at the hardware level, how do you get that much data going through? So videos, they're big, they're getting bigger, and we always need to compress them in some shape or form. All right? So it's going to be a very short lecture today. So there's a number of references to books you can read. I will put online we have handouts from previous years that are totally 100% relevant. I will put them on Blackboard. And these are the two blogs that are very interesting from YouTube and Netflix, because I say probably YouTube and Netflix are kind of especially Netflix are very fanatical about image quality, and they were working hard on advancing the state of compression, and they have very interesting blogs on these websites. All right, that's it.